Alright, in this video, I am going to go over Kirchhoff one more time. You are going to have a question like this during the exam. So what we are going to do, the first thing is evaluate the current in every branch, and then use those current to find the power, the voltage anywhere. So here I have chosen few points. Question 1, what is the current in each branch? Number 2, the power in the 24 volt here. What is the power delivered by this source? And then the voltage across the 40, the voltage here, and the power across the 12. So here is how it works. The first step is to assign plus and minus to every component. So the source is polarized by design. The long arm is plus, the smallest is minus, so plus minus, plus minus. Next, I am going to guess the direction of the current in every branch. Even though I don't know for sure, I can just make an educated guess. By convention, the current leaves the highest end, so I expect this current to move this way. I call it I1. So it's going this way, and it splits, and then it comes back. It's the same current I1. I choose this junction here. So I1 is this, and I decide to walk along this direction, in the same direction as this source. On the other side, I expect the current, this I2, to leave also the positive end. So this is I2, and then we'll split somewhere here. This is I3. So either I use this junction or this one, it doesn't really matter. So at point I'm going to write the junction rule. So I'm going to decide what is leaving is positive, what is coming is negative. It doesn't really matter. So I'm going to say I1 plus I2. So what is leaving is positive. I choose that. Minus I3 is 0. So this is my first equation. My first equation. By the way, I'm going to build a matrix. All right. So junction A. Now, loop 1 and 2. Before I evaluate the loop rule, I have to assign plus or minus to every resistor. Since I decided I1 is going this way, this has to be plus and this is minus. Why? Because the natural flow is down the hill like this. So this is like plus, this is minus. So if I know current is flowing down the hill, this has to be positive, this is negative. It is true for gravitational tilt. It is also true for resistance, like so. If I know the current is going this way, then this has to be high and this is low. That's the idea. Okay, so therefore plus and minus, and here the current is going this way, that's plus and minus, and here the current I3 is going down, so this is plus and this is minus. Okay, just convention. Now I am ready probably to write the loop rule. This is loop 1. So I'm going to choose a point here, for example, and walk along the direction, this direction I choose. Again, all this is arbitrary. It doesn't really matter which way you walk, but once you decide, you have to be consistent. So also I'm going to use the KVL rule convention, much easier to evaluate the voltage change across every component. So here, the idea, you walk and you pick the sign, the first sign you encounter. It is negative, this one. So I'm going to put minus 10. Yes, let's read minus 10 volts. Okay, then I continue. The voltage across R is Ohm's law, R times I. The voltage across R is R times I. R is 40, and so I encounter plus, I put plus 40, and the name of the current is I1. I continue, I encounter plus, the result is 12, so plus, and the name of the current is I3. And this is equal to 0. Now I'm going to rearrange this equation so that I have I1, 2, and 3. So I don't have I2, so that is probably 0. So this is now 40 I1, and then plus 0 I2. I don't have 0, don't have I2, and then plus 12 I3. And I bring the voltage on the other side and change the sign, which is 10. So this is my second equation. Remember, I'm going to build a matrix. Now let's do magenta. Now, what about the loop number 2? I'm going to walk from here and come back to the same point. So I walk, the change is not, there is no change. Then I hit minus and over 24. So minus 24. Again, I'm using the KVL convention. Then I walk. I hit plus, so it's plus. It's plus 10, and the name of the current is I2. That's Ohm's law. That's how you value the voltage. And then I continue. I have plus 12 I3. And this is equal to 0. Now let's rearrange this equation. I don't have I1, therefore it's I1 is 0 coefficient, 0, a plus 10 I2 plus 12 I3, and I bring the voltage on the other side, which is 24. And this is my last equation. All right, now here is my matrix. Here's my matrix. So this 1, 1, negative 1, 1, 1, negative 1. And then in this equation I have 40, 0, 12. 40, 0, and 12. And the last one 0, 10, 12. 0, 10, and 12. So this is my matrix, the coefficient of resistor, and the current vector is I1, I2, and I3. This is equal to the column vector of the voltage, which is 0, and then this is 10, isn't it? It's not 0, this is 10. Yes, you see this 10 here has to be, this one here has to be the other side. So it's 10. And this is now 24. All right. Now, at this point, we are done with the physics. The rest is math. I use Excel. You are welcome to use anything else, probably your matrix or your calculator. So here is, I'm going to use Excel. I hope you can see. So let's do the math then. So this is the matrix, 1, 1, negative 1, and so forth. So this is the same matrix, as you can see. 40, 0, 12, 40, 0, 12, 0, 10, 12, 0, 10, 12. So this is how we do it in Excel. So I select 3 by 3 and equal to call function and matrix inverse. Matrix inverse. And it takes the argument, the matrix A, close, Control Shift Enter. This is the inverse matrix A. The voltage column is 0, 10, 24. The current is 3 currents, so I'm going to select 3, and then it is equal to call the function as multiplication, matrix multiplication. So the argument is a minus 1 and then the column vector of the voltage. Again, close, Control Shift Enter. Let's try again. There is mistake here. So 3 by 3, so equal. So the a minus, and then there you go. So these are the current I1. I can put here I1, this is I2, and this is I3. So I have solved the problem. All right. So now that's notice the negative sign. Probably we have an explanation here. The negative sign, this one here, that means the current I1 is actually this way. And it makes sense because 24 is stronger than 10, so we'll push the current the other way. Everything else is correct. All right. So now let's remove this. So we are going to put the current vector I is I1 is 0.068 amps, of course, and then the I2 1.13, and then this is 1.06 amps. So that's my answer. So we have answered the first question, this one, the current. Now the power in voltage 24. Well, now this is very easy. Since you have the current, the power in the source is the current times the EMF. So the current here is I2, which is 1.3 or 13 times the voltage through across the source, which is 24. So the answer has to be in watt. Let's do the math. So what is it? 1.13, that's I2, times 24. So 27, almost 27 watt. So this is all right. And then next question, this is 2 now. So this is 27 watt. And then the voltage across 40. So the current is I1, which is 0. So the voltage V across 40. The current is I1, which is 0.068 times the current, the resistance 40. So what is this? 40 times 0.068. So 2.7. I'm running volt, of course. I'm running out of time because the video will stop 15 minutes. Now the last question, so we did this. Last question, what is the power across the 12 ohms? Well, the power across the resistor is R times I squared. Since I'm talking about the 12, so this is 12, and then times I squared. The I1 is 0.068 squared. So what is this? So this is 12 times 0.068 squared. All right. So this is so it is equal to 0.05